Rational computing. Checksums Part 2. In the last video, I indicated that in this video we would be decoding the checksum we created. Since then, I've decided that it would be better if we spent this video going over some prerequisites and doing that in the next. The world is a big place. A very big place. And it has a lot of people in it. A lot of those people are mathematicians. And a lot of those mathematicians are far smarter than I am. My first goal in creating a video is to learn the subject better. The second goal is to simplify the topic as much as possible. One of the best ways to do this is to create a simple set of rules, a game, as it were, to follow those rules and to see where it leads. Okay, here we go. Let's give it a try. Here are the rules. We can start with one number. This number can be transformed by shifting it to the right. When we shift it to the right, we decide how many columns it's shifted to and what ratio the existing number is transformed through. In this case, the ratio is 1 and the number of columns is 3. That's it. That's all the rules. This kind of game can be iterated indefinitely. It's fascinating to see where something this simple can go. Notice how every subsequent iteration takes into account the columns of the previous. The columns should be summed in the bottom row. The second row is 2, 2, 1. The third, 4, 3, 2. As we carry on, 7, 6, 4, 13, 11, 7, 20, 4, 20, and 13. After 30 or so iterations, we get these numbers. There are some very rewarding relationships to identify here. We can see that we have a ratio A, B, and C. There are laws that interconnect these ratios. For example, A equals 1 over B plus 1 over C. B equals 1 over C plus 1. And C equals 1 over A plus 1. Also, A equals C over B. B equals C over A. And C equals A times B. Would you be surprised to learn that this simple game gives us the solution for a polynomial? Well, not if you've been watching this video series, but it's true. The ratio C is the real root of the equation x cubed minus x squared minus x minus 1. We have in the past used a similar technique to solve for C. What we haven't encountered in the past are these composite or harmonic ratios that are related to this root C. Understanding these subratios is very important to unraveling how we can actually decompress data from a checksum. This is especially true when we're using a polynomial that's more complex than quadratic. You see, with a quadratic polynomial, we never encounter this phenomena. But as we increase the complexity of our polynomial, it becomes mandatory. This is also a perfect illustration of how losing track of the first principles can stifle our comprehension of a topic, especially as it grows more complicated. This simple game approach is vastly superior to a lot of other methods for approaching a problem like this. Before we finish this video, let's look at this problem abstractly, just to be sure we understand exactly what's going on. It turns out that this table is quite simple. Each column is derived from the first. For example, at the fourth row, the second column is comprised of n2 plus n3, where the third column is comprised of n3. This pattern holds true for all rows. What cracks the code here is to recognize that n4 is also a composite of previous values. The current row of the first column is composite of the 3 previous values. The second column of the current row is composite of the previous two values of the first column. And the last column of the current row consists of the value immediately before the current row in the first column. The exciting part about looking at a problem abstractly like this is now we have the knowledge required to extend this to the right or the left. I'm always curious about what mathematical properties we'll discover as we extend a table like this indefinitely. I'm also really excited to show you in the next video how we can use these ratios to essentially unzip an integer into an entire data stream. It's very rewarding. As I always do, I've written an app that goes along with this topic that helps you explore the subject. It can be found at math.d8data.io, and it's called Seed Functions. It allows us to generate this table with arbitrary configuration. For example, this is 20 high. It also lets us select the initial symmetry, which is useful for certain applications. Have a look for yourself.